I decided to do all of the join-ins for this chapter together. So if you want to pause the video every time I get to one of these slides, because then I'm going to click and get to the answer and explain it. To convert from millimeters of mercury to atmospheres, we use 760 millimeters of mercury for 1 atmosphere. Pause here. Same setup as before, millimeters of mercury to atmosphere, 760 to 1. Number 3, pause the video here. Putting them in order of increasing velocity, the greatest is going to be the lightest. And I looked at the molar masses for H2O, B2H6, and O2, and H2O is the lightest, so it's going to be the greatest velocity. Pause here. Looking at this, we can see here that the lowest speed is A, which is going to be the heaviest. And I looked at the molar masses for all of these options, and the heaviest was xenon. And the fastest, or the greatest speed, is going to be the lightest, which is D, helium. Pause here. The average energy of the helium atoms is the same as that of the neon atoms. Pause here. I looked up the equation for RMS, and I found the molar mass for HCl and the molar mass for NH3. So I found the RMS for HCl, found the RMS for NH3, and this was showing it the RMS for HCl divided by RMS for NH3. So when I did HCl divided by NH3, I got 0.68. Pause here. The one that will diffuse the slowest is going to be the heaviest, and Cl2 is the heaviest. You would need to look up the molar masses for each one of these. Pause the video here. That last section talked about van der Waals equation, and that would be at high pressures and low temperatures where a real gas would behave differently. Pause here. I originally wrote down the volume and the pressure and the temperature for 1, and we needed to find the volume. I wrote down the pressure and the temperature, but then I saw that the temperatures were the same, so I could just leave it out and use Boyle's law, P1 V1 equals P2 V2 to find the volume. If you left it in there, it wouldn't have changed anything. Pause here. Here I was given a volume and a temperature, another volume, and we had to find the other temperature. Keeping in mind that the temperature that we found would be in Kelvin, so I had to subtract 273 to get the Celsius temperature. Pause here. When I used the combined gas logs, I was given temperature, pressure, volume, and I needed to find the pressure to see what happened to it. When I found the pressure, I got 0.458, which would not be any of those options. Pause here. I used the balance equation here, and I saw that for every 1 liter of B2H6, there was 3 liters of oxygen, so it's a 1:3 ratio. Pause here. There are more atoms of helium than neon if there are equal masses, because neon weighs a lot more, so there's going to be a lot more helium to have that same mass. Pause here. If we have equal masses, then the pressure of helium will be greater because there are more atoms of helium since it's lighter, and there will be more bombarding of the sides of the container, so that means more pressure. Pause here. Xenon would have the greatest density because if they all have the same volume, temperature, pressure, then the one that has that greatest numerator, the greatest mass, then it's going to have the largest density, and xenon has the largest mass. Pause here. It'd be a 14:1 because it was reduced from 28/2. Last one, pause. We have a 1:3 ratio, 1:3, and if our total pressure for the mixture is 200, we need to have a 1:3 ratio, so a 50 to 150. Add those two together, it would equal 200. Nice job.